In this video, we're going to examine the world record 100-meter dash of Usain Bolt of Jamaica and use physics to figure out how fast does Usain Bolt run and what is his acceleration. That's coming up today in High Peak Education. Thanks everybody for joining me. Appreciate you all very much for your allegiance and your dedication to this channel and for watching the videos and for supporting our content. So this is a really interesting physics problem where the Jamaican sprinter Usain Bolt set the world record in 2012 in the Olympics, and it turns out we're going to analyze his motion, and by analyzing his motion we'll be able to use one-dimensional constant acceleration linear physics, that is the kinematic equations, and using the kinematic equations, sketching graphs, and then using two equations with two unknowns, we'll be able to actually solve for both his acceleration and his maximum speed. And this is a really difficult Physics 1 problem, but as we'll see, we are able to solve it. So let's go ahead and get into today's content. All right. A world record was set in the men's 100-meter dash in the 2008 Olympic Games in Beijing by Usain Bolt of Jamaica. Okay. Bolt coasted, quote unquote, across the finish line with a time of 9.69 seconds. If we assume Bolt accelerated for 3.00 seconds to reach his maximum speed and then maintain that speed for the rest of the race, calculate his maximum speed and acceleration. So this is almost exactly the same question I gave my students on the final exam. So let me just briefly say, this is not sort of like an easy question. Okay, we're going to need to kind of follow along with this a little bit. We're going to be using what kind of physics equation? Yeah, so what would you call them, or what's the special condition we're going to? My first suggestion is underline the key pieces of information. That's always where we can start, right? So world record set by men's 100-meter dash. Okay, so we're going to underline that. 2008 Olympic Games, blah, blah, blah. Location, name of person, country, coasted. Now it says coasted across the finish line. Think about what coasted means. When Usain Bolt reaches his maximum velocity, so he's speeding up, right? When he reaches his maximum velocity, what do you know about that maximum velocity as he goes towards the finish line? Well, not just for 3 seconds, he's speeding up for 3 seconds. But after he reaches that maximum velocity, he does what? So in other words, he keeps it. He keeps going that fast as he can go until he reaches the finish line. Okay. In fact, usually, if you've ever watched these sprints, right, the sprinters usually make sure they run through the finish line, right? Like they make sure they're still going their maximum speed when they cross the finish line. And it takes them many steps to sort of slow down, right? So coasted means he sped up to his maximum velocity, but then maintained this maximum velocity up through the finish line of the race. That's a key idea. Sometimes when you read these physics questions, I don't want to call it reading between the lines, but you do need to read what it says and understand what concept that it relates to. Okay, so that's what coasted means, right? He sped up. He's going as fast as he can because he wants to get there as fast as he can because he wants to win for Jamaica. And then he keeps up that speed all the way up to the finish line and through the finish line, right? Right. Okay. So let's keep going then. Is that clear so far? Yes. Okay. Across the finish line with a time of 9.69 seconds. Okay, so think about that. That is T total, the total time, right? All right, so that sounds good. And by the way, a lot of times whenever you write something like that, I recommend you write it with a subscript. So let me just go back here a second and write it as T total, like that. So the subscript there is like T is the variable, but the subscript is like kind of the description, right? Okay. If you're keeping it attached to the variable.
Does initial and final, so would total be the final position here, or would it be?
Yeah, good question. What this is going to be is T total is going to be T final minus T initial. But
Right.
here's my question. What do we assume T initial is when we start this race?
0.
Yeah, 0 seconds. In other words, the person timing the race hasn't started the stopwatch yet until the gun goes off and the sprinters start, right?
Right.
Now, in the old days, they used to use like actual stopwatches. Nowadays, it's like electronic, right? It's very
Right.
precise because it's
Mhm.
like up to, again, and pretty incredible, hundredths of a second.
Yeah.
But anyway, you get the idea. Okay, so T initial. And by the way, we typically assume that in physics unless we're otherwise told.
Right.
So
Right.
we assume that all T initial times are 0 seconds unless we're otherwise told. So whenever we get to choose, in other words, we get to do the problem like we want to, I would suggest do it that way. It makes the problem easier. If we assume that a bolt accelerated for 3.00 seconds. Okay, so let's pause there for a second. We assume that bolt accelerated. Let's talk about that for a second. When he accelerates, what do we assume about his acceleration? Do we assume the acceleration is erratic or is it like constant? Yes. So we assume that the acceleration is constant. Now think about what constant means, right? Maybe you might want to look in the camera here for a second because I'm going to show you. Like if your car is accelerating at a constant acceleration, your speedometer looks like this, right?
Right.
It's a nice constant acceleration, right? You're constantly sort of speeding up.
Okay.
Now, for the sake of this class, we usually are going to assume, so let me write this down. We are usually going to assume that accelerations are constant in this class at least 90% of the time or more. Now, the reason for that is because whenever you have a non-constant acceleration, again, I'm not sure if you can look in the camera, but it would look like this in the speedometer.
Okay.
Like it'd be sudden jerking of the car or something, right?
Yeah.
So that's a little harder to deal with, and that's a little harder to calculate with.
Okay.
So what I'm saying is that when we assume these constant accelerations, it turns out we can write down certain equations in physics in terms of the constant accelerations. Okay? In fact, do you know what those equations are called? So they're called the constant acceleration kinematic equations. Does that sound familiar from class? I hope.
Yeah, it does.
Okay.
I
The
was gonna say
constant
good.
acceleration kinematic equations. So the kinematic equations are equations that relate various motion variables to one another.
Right.
And they're equations that basically can be derived as long as you assumed constant acceleration. You had to assume that. So it says if we assume Bolt accelerated for 3.00 seconds, let's just assume that acceleration is constant, okay?
Okay.
Now, by the way, there's going to be, how many time periods are there going to be in his race? Now, by the way, one other thing I also recommend is whenever you're trying to get your head around a somewhat difficult problem, by the way, I do notice that this is a multi-part question, okay?
Mhm.
So a multi-part question means you really need to solve for various things to use later. So we're going to have to kind of do that here. So whenever it's a relatively difficult question, I recommend, in order to get your head around this, you do draw a little picture. So let's just draw a little picture of what the race might look like here. Okay. So here's the race, right? And then here's Usain Bolt. Okay.
Mhm.
So this is the 0 meter line. What would this line here be when he finishes the race?
100 meters.
100 meters, exactly. Okay. In fact, since it's a 100-meter dash, why don't we call this delta x total is 100 meters.
Okay.
All the way from here to here. Okay, that's delta x total. It's the total displacement. Okay, because that was actually mentioned before. We underlined that, but now we're sort of labeling it.
Okay.
The reason I mention that, though, is because there's sort of, I want to ask you, how many time periods are we going to sort of split this motion into?
2.
Yes, good. So up to here, what is Usain doing during this time period?
Is accelerating.
Yes, good. He's accelerating here. Now during this time period, he's doing what? We already kind of set it up here on the upper right. Exactly. He's maintaining his maximum, you should say, maximum velocity. Do you see that?
Yeah.
So for simplicity, why don't we call this time period 1 and this time period 2? I don't recommend you call them initial and final. Call it period 1 and period 2.
Okay.
Also, you could call it period A and period B, whatever you like, but let's just do 1 and 2, okay?
Okay.
All right, so is that clear? Because now we're really getting somewhere. Here's my next question. How long does this time period take? What's delta T1?
3 seconds.
Yes, do you see that? It's labeled right there. This is 3.00 seconds.
Mm-hmm.
So let me ask you this. How long from here to here is delta T2? Right, it's just the difference between 9.69, the total time for the whole race, and the 3.00, right?
Mm-hmm.
So that would be what, 6.69, I guess, seconds? Okay, we're getting somewhere now. So think about this. We have the total distance, total displacement, I should say. We have the time for segment 1. We have the time for segment 2. And we know in segment 1, we're accelerating.
Mm-hmm.
And we know in segment 2, we're at maintaining a maximum velocity. Okay? So in fact, let me ask you this about segment 2. What's the acceleration of segment 2? Yes, good, 0. 0 meters per second squared. So keep in mind, that is a constant acceleration. It's just a very special number.
Okay.
0 is very convenient to work with.
Mm-hmm.
Let me ask you another question, which is sort of intrinsic, but we definitely have to write this down. So I want to just make right here where Usain is standing, I'm just going to put a star, and I'm going to over here star. That's at the starting line. What is the initial velocity of Usain Bolt at the starting line?
0.
Yeah, it's got to be 0, right? Because he starts from rest. Now that's somewhat obvious, but it's important that we write these things down because then we can start using those numbers. It's even important to write down the zeros. Okay, does that all kind of make sense?
Yeah, it does.
Okay, so now I think we should really kind of get into the meat of the problem, okay? Because it's kind of like we've laid it all out. We've got all our instruments. We've got the patient cut open. Now we're going to kind of go in and do the thing, okay? So let's think about this. There's one, I think, key idea that we haven't mentioned that's a concept that I think we need to identify in order to relate the equations together. And let me try to explain this in terms of like maybe a sketch of a graph. So suppose this was the position versus time. I'm sure you've seen these in your class so far. X versus t. Okay? So this is position versus time. Why don't I do segment 1 here in red? Segment 1 is going to look like this, where he's accelerating, right?
Mm-hmm.
So this is all segment 1. But then in blue, I'll do segment 2. He's maintaining a constant velocity, so he's going like this. But then we know, this is important, we know that right up here, this point is 100 meters, right? Because we get up that vertical axis, we get to 100 meters, we're done the race.
Right.
But here's my question. What's unique or what's important about this point? So first of all, what is the time at this point? We already kind of talked about that.
3 seconds.
This is at 3 seconds. Okay, that's a very important time. And here's such a key idea, but we have to make sure we write this down. What is true about how we tie segment 1, and I didn't label it in blue, I meant to, segment 1 and segment 2 together as it relates to what happens at 3 seconds.
Say that one more
Yeah.
time.
How do we tie the motion of segment 1 together to the motion of segment 2 as it relates to that important time of 3 seconds? So think about this very carefully. Usain is accelerating in segment 1 up to 3 seconds. He
Right.
reaches his maximum velocity. So think about this. Listen carefully. That's like the final velocity of segment 1. Hear that? Final velocity of segment 1. But the final velocity of segment 1, which is his maximum velocity that he maintains
Right.
once he gets there, is also the initial velocity of
Segment 2.
segment 2.
Okay.
Now that we lay that out, that might seem a little obvious, but that's not obvious until you write it down. So let's write this down. This is so key. So we say the final velocity of segment 1, I'll do the quotes, 1, is the same as the initial velocity of segment 2. Segment 2. Okay, let me hit done on here. Okay, this is really important that you understand that, right? Another way to think about this is that, do you see that the slope here is the same as the slope here? I'm assuming your professor has talked about slopes a little bit before, of these position versus time graphs, right? This slope and this slope are exactly the same as he gets to his maximum velocity. And it's not just the final velocity of segment 1 is the same initial velocity of segment 2. You could even say, in fact, that velocity is Vmax, the maximum velocity, right? That's such a key idea. So now that we have all that laid out, I'm going to recommend we start finally writing equations. When we start writing equations, I went over to page 6 now. When we start writing equations, we need to think about which equations are going to be most useful in terms of the kinematics equations and which ones we can kind of tie together. What are the 5 kinematics variables that we often deal with? Yes, time is one of them.
Acceleration.
Acceleration's one of them, yep.
Velocity.
Yep. And let me pause you, not just any velocity, which velocities?
Final and initial.
Right, so we have an initial and a final velocity, and there's one more variable. So,
Position.
yes, in fact, displacement. Okay?
Displacement. Yeah.
Exactly. So, and by the way, position is correct. Position is just where you're positioned right now. Displacement is your change in position.
Right.
Okay. So you're essentially correct. So these are our 5 kinematic variables. Now, by the way, I would suggest, again, I've done this problem before, but I know you haven't. So let's do a little accounting in terms of, let's figure out which variables we have and we don't on segment 1 versus segment 2. And just following along with the colors, I'll do segment 1 here in red, and I'll do segment 2 here in blue. Okay? And I'll put like a little wall between them. Okay? And all I'm looking for here is check marks. Like, let's just do some accounting and see what we have.
Okay.
Do we have the initial velocity of segment 1?
Yes.
Yes, so put a check mark. Do we have the final velocity of segment 1 yet? Not yet, but we probably want to calculate it. So let's put a question mark here because this is important that we calculate that because this is going to be Vmax, right?
Right.
We've already talked about that. Do you see why it's nice that we talked about it already? Because it's going to start to unfold itself. Do we have delta x of segment 1? No, not specifically. We have the total delta x.
Yeah.
But we don't have it for segment 1.
Right.
So let's just say not fully.
Okay.
We sort of have it in part, maybe, but we might need to go back and get it.
Okay.
Do we have the time for segment 1? Yes, we do. Now, do we have the acceleration? How much he accelerates for segment 1?
No. Well, no.
No. And it turns out, by the way, if you closely read the problem, that's actually one of the ultimate goals.
Yeah.
We do want to know what his acceleration was in that first 3 seconds. So why don't we put a 2 question marks here? Because this is one of our ultimate goals, Vmax, and then this is the other ultimate goal, the acceleration.
Okay.
You follow me?
Yes.
Okay. Now, I know we've been a little pedantic here. We can speed up maybe a little bit, but we're believe it or not, we're really almost there in terms of laying this all out. Do we know the initial velocity of segment 2? No, but do we know it's related to something else? Yes. Do you see why it's important to kind of put this arrow here? It's the same thing as the Vmax.
Yeah.
Okay. Is the final velocity of segment 2 related to the initial velocity?
Yes.
These should be the what?
Same.
The same. Okay, so that's important. We write that down, right? They're the same. Do we know the delta x of, again, segment 2?
No.
Yeah, again, not fully, right? But we'll come back to that. Do we know the time of segment 2? Yeah, we do. Okay, so there we go. And then do we know the acceleration of segment 2?
Yes.
Yes, we do. And it's 0, right?
Mm-hmm.
Okay, so think about this. On each side, you have 2 knowns on each side. 2 knowns on each side. Now, I'm sure we'll go over this very soon, but the way these kinematic equations work, I figure I should write this down because you probably need to know this anyway, but it's worth mentioning. I mean, you're kind of starting off with a difficult problem, which, you got to know how to do it. But what I was just going to say is the way the kinematic equations work, you need to have 3 variables known, then solve for the 4th, knowing which variable you are going to ignore. Okay? So generally, whenever you look at those kinematic equations, there's always 4 variables in the equation. You have 3, you can solve for the 4th, but the 4th that you solve for is dependent upon the variable that's ignored.
Okay.
Now, in this case, we only have 2 knowns on each side, but we do know also that they're tied together via the Vmax,
Mm-hmm.
and we can get a single equation from which variable? Which variable do we not know fully for column 1 or column 2, but we do at least know the total? The displacement, right. The change in position, exactly. So think about this. Does it make sense to you, just thinking about like the logic of numbers, that delta x1, the displacement for segment 1, plus delta x2, which is the displacement for segment 2, should just be the same thing as delta x total?
Right.
Does that make sense? No matter how many meters segment 1 and segment 2 are, we know that they at least add up to 100. It's a 100-meter dash, right? So it's got to work itself out that way. So what I'm saying is this is a useful equation. We probably want to use this equation.
Okay.
Now here's what we want to do. We want the equations, the kinematic equations, that can give us a delta x, like delta x1 or delta x2, but we want them in such a way that we only get one single variable, or we want to reduce it down to one single variable. So what's one of the kinematic equations that has delta x on one single side? Yes, plus what else? Plus 1/2 at squared. It turns out this equation is if you're accelerating. Okay, so this is sometimes called the displacement curve. By the way, part of the reason it's called the displacement curve, I'm going to toggle back to board 5 for just a moment. Part of the reason it's called the displacement curve is, do you see how the red curves up?
Yes.
Okay, the fact that it curves up is given because it's essentially a quadratic. And you see that this right here is quadratic, like the t squared. Okay, so you remember those from algebra, right? Parabolas and all that. But anyway, the reason I mention that is because the displacement curve is this displacement as long as you're accelerating. Now, what's unique about segment 2? In segment 2, whoops, too many quotes. The acceleration is what number? We already said it right there. It's 0.
Yeah.
Right. So the thing is, in segment 2, this last term is just equal to 0.
Okay.
So here's what I'm saying. Let's just write down delta x1 and delta x2. Delta x1 should be v initial of segment 1 times t1. You see how I'm doing subscripts? Subscripts is important.
Yeah.
Plus 1/2 a times t1 squared. Notice I'm not just doing any t, I'm doing t1, only of segment 1, right?
Right.
Now, for the second part, we're going to do plus, let's see, v initial, or sorry, not v initial. This is going to be v max, right? Because we've already talked about that, right? He's running at his maximum velocity.
Right.
V max times t2, he runs for time t2 in segment 2. And then remember, it's going to be plus 1/2 a t2 squared. But since this is 0, what do we know about this entire term? Right, just v max times t2. So this term is 0.
Right.
In fact, by the way, we can make one more simplification. What do we know about v initial here on segment 1?
It's 0.
Right. So one thing I also recommend is I recommend you do all the symbols at first, but if anything's 0, I also recommend you knock that out.
Okay.
Just makes the algebra a heck of a lot easier, right?
Yeah. Right.
So anyway, we should just be able to say 1/2 a t1 squared plus v max times t2 is equal to delta x total. Now think about that. That's not that difficult of an equation, right?
Right.
1/2 a t1 squared plus v max t2 equals delta x t total, right? Notice we have this, we have the times, but we just don't have, this is the double question mark, and we don't have this, the single question mark. So here's the deal. We have one equation, two unknowns. Let me write that down. One equation, two variables. You can't solve that, so we need another what?
Equation.
Yeah, we need another equation, right? Because this is hopefully something you learned in algebra, right? If you have two variables, you need two equations, right? This is what's called a linear system, right? You've probably heard this before, good memories and all that, right? But anyway, you get the idea. So we need another equation. So I'm going to go on to the next board. So let's write this down. We need another equation in order to solve for either, let's see. So to solve for either A or V max, right?
Right.
So we're almost there. Now, let's think about this. Is there another way we could get A in terms of V max or V max in terms of A? Now, by the way, this is the other, one of the mental, in my opinion, one of the mental leaps that you needed to make in this problem is that the final velocity of segment 1 is the initial velocity of segment 2, right? And that's the V max.
Right.
Now, I'm now asking you to make the second mental leap. The second mental leap is a non-obvious, but if you think about it, you might be able to get it. How is the acceleration related to the maximum velocity? There's another kinematic equation that says V final is equal to what? V initial plus AT. Does that look familiar?
Yeah, I just don't know them yet.
Okay, no worries. Okay, and that's why they're in your notes.
Okay.
And we'll talk about them, okay? This is often called the definition of acceleration equation, okay? The definition of acceleration equation. Now, the reason I bring this up is because can we use this one? Notice I did it in red specifically. Can we use this one for segment 1? Well, I wouldn't be telling you unless the answer was
Yes.
Yes, right?
Yes.
Okay. So yes. And let's think about what this is going to be. V final for segment 1. Now let's make this all segment 1, right? A and then time 1. Okay.
Okay.
What's V final for segment 1? We've been calling that V max, right? That's the fastest speed. So this is just V max. What's the initial velocity of segment 1? We said that on the previous slide. It's what? 0. So this term just bye-bye.
Okay.
Okay. Equals AT1. Hey, wait a second. I'm starting to get excited. Can I replace Vmax in terms of another variable that I do know? In fact, let's go back to board 6. Watch this. Watch this. Vmax, Vmax can be replaced in terms of A. Do you see that right there? That is the second mental leap. Do you see that you're not stuck with one equation, two unknowns? You can substitute in for maximum velocity in terms of acceleration, then solve the acceleration. Then once you have the acceleration, you can go back and figure out what's his maximum velocity.
Okay.
Does that make sense?
I don't know how to do it on my own.
Again, I gave this as a exam 1 question to my class, like almost this exact question. So if this feels a little hard to you, don't worry. I mean, this one definitely requires a little bit of real gusto.
Yeah.
Okay. But
Okay.
hopefully I'm walking you through it. You're seeing the connections of the ideas. All right.
Yeah.
And for Vmax, what are we going to put in? We're going to put in AT1, right? So we've got A times T1. And now we start to jump for joy because that's one equation with one unknown. What is the unknown in this equation now? So A is unknown. Now, here's another important thing. This is a quick algebra note. In fact, it's such an important algebra note, I should write this down. Let me write it down over here. Whenever the unknown is trapped, I'm going to call it trapped, in more than one term, you need to something it out. So whenever the unknown is trapped in more than one term, so do you see that A is here and A is here? It's in more than one term. We need to, what's the algebra thing I'm thinking about?
Cancel it out.
Not cancel.
Factor it out.
Yeah. Do you remember this?
Yes.
Like I'll change to green color or sorry, pink color or something. Quick aside, right? A lot of algebra students have trouble with this, but hopefully you remember if you have x plus xy equals 1, how do you solve that for x? The key is you have to factor x out, and then the problem presents itself. Do you see it now? Because x times 1 plus y, you just have to then divide by what's in parentheses. I kind of feel like that's an algebra skill that's often glanced over way too quick, but it's worth mentioning. The point is we're going to have to use it. Okay. So whenever the unknown is trapped in more than one term, and we're going to see this many times this semester in physics, we need to factor it out. So let's factor out the A, and then we've got 1/2 T1 squared plus T1 T2 equals delta X total. Okay, did we see how we're going to solve this now finally? Okay, so we're going to get A equals, and then you tell me what should it look like? Delta X total on top, yeah, exactly. Do you notice that the units of delta X total is meters? And do you notice what the units are downstairs? It's seconds times seconds, which is really seconds what? Squared. So isn't this going to be meters per second squared?
Yeah.
I mean, who knew, right? The units work out. I mean, but again, if it didn't, you would have done something wrong.
Right.
I mean, that's a good check, okay? Just kind of that sanity check, like, am I doing the right thing? Okay, so finally, let's put the numbers in, shall we? All right, so let's put the numbers in. So we've got delta X total is 100 meters exactly, right? Then measure that out accurate to like less than a centimeter. Let's see. Then we need 1/2. Now, by the way, 1/2 is the same thing as 0.5, right? So I'm just going to do 0.5. It's easier to put in our calculator. T1 squared, that's 3.0 seconds. squared plus 3.00 seconds times, and then the other time, I think that was, what was it, 6? Yeah, 6.69. 6.69 seconds. Okay, because that was what? The other part of the time takes us up to 9.69, right?
Right.
Okay, so let's get this number for A. Okay, so calculator's out. All right, so we need to take 100 and divide that by 0.5 times 3 squared plus 3 times 6.69. Okay, let me know when you get an answer. That's what I got. 4.07. What's the units? Meters per second squared. Good. Okay, so that's one of our answers. By the way, if you just want to think about how incredible Usain Bolt is, you know, the acceleration due to gravity is about, I'm not sure if you talked about this in class yet, it's like 9.8.
Yeah.
Right? That's almost half of gravity. I mean, think about, that's incredible, right? This guy can push his body forward, speeding up almost half of what the Earth can pull you down, like off of a high dive.
That's wild.
I mean, it's just absolutely incredible what the human body can do after lots of training. Anyway, but now let's go back and get Vmax. Now here's the deal. Vmax, we should already have an equation that's like well suited for Vmax. It's the equation that we already substituted in. Do you see that this equation right here, we can solve for Vmax very easily?
Yeah.
Very easily, right?
Yeah.
So we can just say Vmax is, what is it, A times T1. That's pretty straightforward to calculate. A is 4.07 meters per second squared times the time 1 of 3.00 seconds. Okay, so let's put those in the calculator. So we just need, let's see, 4.07 times 3. So what do you get? Yeah, so let's round it to 12.2. So it's 12.2 meters per second. And I'm just going to ask Siri, how many miles per hour is 12.2 meters per second? 27.29 miles per hour. Again, kind of like I mentioned before, right? Absolutely incredible how fast this man can run. Yeah, good question. So part of the reason is yes. But secondly, look at this. Look at these units. Do you see I have meters per second squared times seconds? So what happens to one of the seconds?
One of them cancels out.
One of them cancels out. That's right there and right there.
Okay.
See that?
Yes. Yeah.
Okay. Now, by the way, after a long problem, I usually recommend we spend about 30 seconds and go back because it's hard to see the forest for the trees, right? Like, and then that way you actually understand what we did because we did so much work here, okay? So let me just briefly say out loud, what did we do? It was a 100-meter dash. He coasts across the finish line because he's moving at its maximum velocity. We know what the total time was. We also know how long he accelerated for. The acceleration time, we're calling that segment 1. The maximum velocity time, we're calling that segment 2, as you see sketched down here.
Right.
We know that he starts from rest, and we also know that he's not accelerating in segment 2, and we figured out the times for each segment. One of the major leaps was that the final velocity of segment 1 was the initial velocity of segment 2. And in fact, it's also his maximum velocity, and he just maintains it. And then what we did is we said, okay, let's write an equation from that, from the kinematic equations. Delta x total is delta x1 plus delta x2. In the first displacement curve, we knocked out the initial velocity because he starts from rest. In the second displacement curve, we knocked out the acceleration term because he's not accelerating. We put those in. We had one equation, two variables, so we needed another variable. In order to do that, we used the definition of acceleration. We found the final velocity of segment 1 is Vmax, AT1, substituted it in. We had to factor out the A, solved, put the numbers in. Once we had A, we could go back for the Vmax equation. We could find Vmax by just plugging in A in time 1, and we got his maximum velocity. I mean, I wish it was easier, but that's how we have to do it. I mean, does that make sense, though? Right. And by the way, like I totally understand that. Like it's a total legitimate like kind of that internal anxiety thing. But let me just say again, I don't anticipate, number one, most questions being this hard,
Okay.
especially on an exam. Like in an exam, like my students would have 3 hours, and this was like by far the longest question on the whole exam. And they also got partial credit, and it was like 5 parts, and like each part was like worth several points.
Okay.
So just giving you a little bit of comfort.
Yeah.
Second thing I'll say is part of the reason this is a multi-step problem is because you had to tie one list of kinematic equations to another one. Like what's in red and what's in blue, those are tied together. And
Right.
that typically means the problem is a little harder. Number three, you also just know that the more you do it, the more it will become second nature. So some of this is just going to be practice. Like, so the practice part of it is saying, okay, like, how is it that I can tie these things together if I look at the analysis? So now, amazingly, we can actually solve for the acceleration of Usain Bolt and his maximum speed. So who knew that only from knowing the distance of the race, well, 100 meters, and the time it takes for him to accelerate, and as long as we assume he keeps moving at a constant velocity at his maximum velocity, we can solve for what that maximum velocity is. By the way, think about this. Usain Bolt is moving more than 27 miles per hour. That is absolutely amazing. He can actually outrun several species of animals. Absolutely mind-blowing what the human body can do under rigorous training and preparation. So I just want to commend Usain Bolt on an amazing world record. And I want to commend you and thank you for taking a look at this physics video. Let us know in the comments how you're going to use this information. Is it for human performance? Is it for your curiosity in terms of the ability of a person to run fast and your interest in the Olympics? Or is it as a student of physics when you're solving one-dimensional motion problems? Go ahead and let us know in the comments. And thank you for watching High Peak Education. Please smash that like button if you enjoy this content. Please subscribe to the channel in order to grow the channel. Social media links are down in the description. Please support us on Patreon. I want to thank you for your time watching this video, and I will see you in the next video.